Welcome. This course is about proof systems. A good way to think about it is this: computers are built from switches, zeros and ones, and logic is the language we use to describe how those switches combine and how conclusions follow from assumptions. From Aristotle's syllogisms to modern hardware design, artificial intelligence, databases, and program verification, logic is everywhere in computer science. In this course, we are not mainly studying those applications. We are building the foundation, how to decide truth mechanically, and how to prove statements symbolically one step at a time. We begin with propositional logic. A proposition is a statement that can be true or false. For example, Alice is an architect is either true or false. In this simple setting, there is no third option. Such indivisible statements are called atomic propositions. Real statements are more complex, so we combine atomic propositions with connectives, not, and, or, and, if, then. The key point is that propositional logic does not look inside atomic propositions. It only cares whether each atomic proposition is true or false. Now we ask which strings of symbols count as legal formulas. We cannot write symbols randomly. We build formulas by rules. First, true and false, and variables are formulas. Second, if F is a formula, then not F is also a formula. Third, if F and G are formulas, then the conjunction F and G and the disjunction F or G are formulas. This is an inductive definition. It matters because later, when we prove properties of formulas, we will often prove them by following this construction from simple formulas to complex ones. Let us translate the common connectives into ordinary language. A implies B means if A holds, then B must hold. The surprising part is that if A is false, then the whole implication is counted as true. This is called vacuous truth. A if and only if B means both directions hold, so A and B are equivalent. A exclusive or B means exactly one of A and B is true, exactly one side is true. Finally, remember precedence negation binds the tightest, then and, or, and implication and biconditional bind more loosely. Parentheses are your friend. Formulas can be written in many different shapes, which is inconvenient for algorithms, so we standardize them. CNF, conjunctive normal form, is NN of ORs. Clauses connected by conjunction, with each clause being a disjunction of literals. DNF, disjunctive normal form, is the opposite shape and or of ends. These forms are important in automated reasoning because many algorithms expect a formula in a standard format, especially CNF. Because formulas are defined inductively, every formula naturally forms a tree. Variables sit at the leaves, and connectives sit at internal nodes. Structural induction follows that tree. To define a function on formulas, first say what it does on leaves, then say how to combine the values from subformulas. Counting symbols, finding subformulas, or generating a syntax tree can all be done this way. When you see induction on the structure of a formula, think climb the tree from the bottom up.